The field of modern air combat is a crucible where victory is defined not by the blunt application of firepower, but by the exquisite, almost molecular precision of engineering detail. In this high-stakes domain, the fate of global geopolitical balances can hinge on factors so minute they are invisible to the naked eye. The specific geometric alignment of a radar-deflecting surface, the microscopic tolerance within a turbine blade, or a solitary critical line of code within a vast, complex algorithm. This is the reality of fifth-generation warfare, a contest fought in the invisible spectrums of radar and heat, and powered by data rather than mass. Nowhere is this struggle more evident than in the development and deployment of the Chengdu J-36, an advanced multi-role fighter designed to project China's nascent naval power and simultaneously challenge the dominance of the established Western benchmark, the Lockheed Martin F-35 Lightning II. The J-36, known in its developmental phase as the FC-31 Gyrfalcon, has rapidly evolved from a privately funded demonstrator into a core component of the People's Liberation Army's Strategic Aviation Doctrine, giving rise to its current operational designation, the J-35 or J-36. This aircraft embodies Beijing's determination to achieve technological parity in the most sophisticated arena of military technology, prompting critical global defense analysis of where its strengths lie, and crucially, where its inherent compromises introduce vulnerabilities. The confrontation between these two stealth titans is a defining moment in modern military history. Some believe the J-36 will rival the F-35. Others dismiss it as overhyped. And you, where do you stand? Type yes or no in the comments. Fact 1. Genesis, adaptation, and the dual-track strategy of accelerated power projection. The story of the J-36, or more accurately the naval variant J-35, is a profound narrative of strategic adaptation and organizational agility. Unlike the F-35 program, which traces its origins back to the cumbersome, consensus-driven Joint Strike Fighter effort of the 1990s, a sprawling $1.7 trillion multinational endeavor burdened by the requirement to satisfy 3 United States military services and multiple foreign partners, the FC-31 began life around 2012 as an apparent proof of concept and speculative export contender. This initial private funding allowed for rapid, focused development, unencumbered by the diplomatic or bureaucratic compromises that often inflate costs and restrict performance parameters in Western programs. This flexibility allowed the platform to be rapidly validated and subsequently absorbed into the central state strategy. This transition created China's essential dual-track stealth doctrine, positioning the J-36 as the medium, flexible counterpart to the heavier, long-range Chengdu J-20 Mighty Dragon. The ability to rapidly incorporate a viable, mid-sized stealth platform into the national development stream demonstrated an institutional agility that many slower, more regulated Western aerospace industries often envy. The design's strong resemblance to successful Western concepts, such as the F-35, suggests a highly effective capacity to analyze and integrate external design knowledge, a rapid iteration capability that translates effective aerodynamic and shaping concepts into a tailored domestic framework far quicker than traditional research and development pathways allow. The most significant strategic mandate for the J-36, however, was its adaptation into the carrier-based J-35. This naval pivot, with its prototype conducting maiden flights as early as 2021 and the land-based J-35A following in 2023, is crucial for equipping the Type 003 Fujin-class aircraft carriers and future naval air wings. This specialization for carrier operations, contrasting with the F-35's multi-service compromise, reflects China's vision for a stealth ecosystem designed specifically for regional power projection. The necessity of adapting a land-based design for the rigorous demands of carrier duty which includes strengthening the airframe, designing for folding wings, and installing arresting gear, comes with a significant structural cost. Navalization naturally increases the aircraft's maximum takeoff weight, reportedly jumping from an estimated 25 tons to approximately 28 tons. This structural penalty, a 12% increase in mass, created a profound engineering hurdle. The initial power plants were no longer adequate, necessitating a radical leap in propulsion technology to ensure the J-35 could operate effectively from a crowded flight deck and achieve competitive combat performance. This challenge directly underpinned the next critical developmental step. Fact 2. The thrust equation, power, and the supercruise ambition. The most immediate challenge facing the FC-31 prototype was its engine performance. Early iterations utilized less powerful, likely imported Russian or first-generation indigenous turbofan engines. This perceived lack of power was considered a major weakness, limiting the aircraft's acceleration and sustained speed. A stealth fighter is useless if it cannot rapidly seize the initiative or successfully evade energy-sapping maneuvers. The weight increase mandated by the naval variant only exacerbated this deficit. The decisive technical solution to this critical performance gap was the integration of twin new-generation WS-19 engines. These power plants are a significant technological achievement, estimated to deliver a maximum thrust of 110 kilonewtons, or approximately 24,000 pounds of force, with the afterburner engaged, totaling 220 kilonewtons of thrust. To understand the effect of this upgrade, one must consider the thrust-to-weight ratio. For those unfamiliar with aviation terminology, this ratio measures the aircraft's brute strength, how much force the engines can generate relative to the machine's mass. A ratio significantly above 1.0 is the aviation equivalent of having reserve energy. The aircraft can accelerate even while climbing vertically. The heavier, carrier-compatible J-36, powered by the twin WS-19 engines, achieves a thrust-to-weight ratio around 1.07 when configured for a light air-to-air mission. This kinetic superiority is the difference between a high-performance sports car maintaining speed effortlessly on a steep mountain incline versus one that strains and loses momentum. The J-36 holds excess energy. This dramatic boost in thrust changes the J-36's strategic mission profile. The high thrust-to-weight ratio strongly suggests the airframe is aerodynamically optimized for supercruise, which is the ability to sustain supersonic flight, speeds faster than sound, for extended periods without engaging the fuel-guzzling afterburner. The ability to supercruise, a hallmark of elite air superiority fighters like the F-22 Raptor, allows the J-36 to dictate engagement timelines, traverse vast oceanic distances quickly, and conserve fuel during high-speed patrols. The J-36 is estimated to reach a maximum speed of between Mach 1.9 and Mach 2.0, that is, nearly twice the speed of sound. This kinematic performance makes the J-36 potentially faster and more capable of sustained high-speed flight than the single-engine F-35, which typically relies on afterburners to briefly reach its maximum speed of Mach 1.6. The J-36's design philosophy, therefore, leans heavily toward speed, acceleration, and energy management, giving it a potential kinetic edge in beyond visual range intercept missions and extended operational radii, estimated between 1,300 and 1,350 kilometers. Fact 3. The geometry of absence and the infrared flaw. Despite its kinetic strengths, stealth remains the cornerstone of any fifth-generation fighter. Low observability is achieved through a meticulous combination of external shaping and specialized materials. Stealth shaping, as one designer dryly noted, is the process of designing a very bad antenna that ensures incoming radar waves are scattered away from the receiver of the detecting radar. This is coupled with advanced radar-absorbing materials that dissipate residual electromagnetic energy. The J-36's shaping has clearly drawn lessons from the successful principles observed in the F-35, resulting in an impressive, though not industry-leading, radar signature. Analysts estimate the J-36's frontal radar cross-section to be in the range of 0.007 to 0.01 square meters. While highly secretive program figures must always be treated cautiously, this figure represents a massive leap over previous generation aircraft such as the F-15, which presents a truck-like 25 square meter radar cross-section. State media proudly proclaimed that the signature was smaller than a human palm. However, this figure suggests the J-36 maintains a slight but critical visibility deficit compared to the F-35, which targets a benchmark of 0.001 to 0.005 square meters. The greater vulnerability in the J-36's stealth profile, however, stems directly from its kinetic advantage. The fundamental engineering trade-off for utilizing twin, high-thrust WS-19 engines, which enable supercruise, is a significant penalty in the infrared signature. Every jet engine creates a colossal heat plume, and managing this thermal emission is crucial for defeating modern infrared search and track systems. Sophisticated stealth aircraft like the F-22 Raptor or the B-2 Spirit bomber utilize heavy, complex heat diffusion mechanisms such as saw-toothed nozzles or methods to thoroughly mix hot exhaust gases with cooler ambient air to rapidly minimize the thermal signature. The J-36, by necessity of its twin high-performance engines and its high-speed mission profile, generates a larger and hotter thermal plume compared to the single-engine F-35. This thermal emission constitutes a major flaw in its otherwise low observability. In a hypothetical high-end engagement, an adversary utilizing advanced infrared search and track systems, which operate entirely passively without emitting energy that the J-36 could detect, could potentially spot the Chinese fighter's thermal wake at crucial beyond visual range distances, effectively neutralizing the J-36's radar stealth advantage. The J-36 prioritized energy and speed, and thermal invisibility was the cost of that choice. Fact 4. The depth of the magazine and the beast mode dilemma. In fifth-generation combat, stealth means that weapon carriage must be confined to internal bays, as external ordnance immediately transforms a low-observable fighter back into a highly visible target. The J-36 exhibits a clear advantage in its internal magazine depth, a capability that enhances its endurance and tactical flexibility in contested airspace. The J-36 features a lengthy centerline internal weapons bay, estimated to be approximately 7.6 meters, or about 25 feet, long, flanked by two smaller bays. The crucial engineering specification is its capacity. The airframe is optimized to carry up to 6 beyond visual range air-to-air missiles internally. This is a key differentiating factor. By comparison, both the F-35 Lightning II and the heavier J-20 Mighty Dragon are typically limited to an internal loadout of 4 beyond visual range missiles. This superior magazine depth means the J-36 can engage more targets, sustain a longer fight, or fire more complex salvos against a single high-value target while fully retaining its low observable status. The primary weapon housed within this extensive bay is the formidable PL-15 active radar homing missile, a weapon capable of reaching speeds exceeding Mach 5, more than 5 times the speed of sound, with an operational range of 200 to 300 kilometers. The ability to deploy 6 of these long-range missiles provides the J-36 with a strategic advantage in beyond visual range engagements, where the ability to saturate an opponent with simultaneous threats is paramount to mission success. Furthermore, the substantial 7.6-meter length of the primary bay suggests a deliberate design decision to future-proof the platform, allowing it to house forthcoming, potentially longer-range weapons such as advanced hypersonic air-to-air missiles or large air-to-surface munitions. However, the J-36 shares a critical tactical compromise common to all stealth platforms: the beast mode dilemma. The aircraft is equipped with 6 external wing hardpoints, allowing it to carry a total payload of up to 8,000 kilograms. In this maximum payload configuration, the J-36 could carry up to 12 or more missiles, transitioning into beast mode. This choice, while maximizing firepower, instantly negates the aircraft's stealth advantage. This trade-off is often conceptualized as the difference between a submarine, stealthy with limited internal capacity, and a surface destroyer, exposed with massive external firepower. Beast mode is therefore reserved strictly for non-contested airspaces or missions focused on maximizing strike payload, accepting the high risk associated with shedding the low observability that defines its generation. Fact 5. The algorithm challenge and the digital brain gap. In the modern air environment, the decisive advantage is no longer found solely in the airframe's aerodynamics or the engine's thrust, but in the aircraft's digital nervous system. The hardware of the J-36 is clearly advancing toward parity with Western systems. It features a sophisticated avionics suite, including an indigenous active electronically scanned array radar, an infrared search and track system, and distributed sensor apertures functionally comparable to the F-35's distributed aperture system. Chinese developers have claimed that their radar system, while smaller than the F-35's radar, boasts comparable combat capabilities. However, the true technological chasm between the J-36 and the F-35 lies not in the radar dishes or the sensors themselves, but in the complex underlying sensor fusion software, the digital brain that conducts the orchestra of data. Sensor fusion is the critical process of taking vast, often contradictory streams of raw data from every onboard sensor, radar returns, passive electronic monitoring, infrared thermal tracks, and instantly synthesizing them into a single, cohesive, three-dimensional picture of the battle space for the pilot. The F-35 is the current global benchmark in this domain. Its system architecture is built upon a colossal foundation of code. The F-35's initial flight control software alone was estimated at 5.7 million lines of code. Crucially, the F-35 has benefited from over a decade of iterative software refinement, continuous testing, and the assimilation of vast amounts of combat data from multiple nations, leading to highly mature upstream data fusion techniques. This extensive operational history means the F-35 software has learned, adapted, and been validated against countless real-world failures and anomalies. The J-36, in contrast, is still in the emerging integration stage. Its digital architecture is undergoing intensive optimization and real-world testing. Developing flawless, robust software that can manage contradictory data under the intense stress of combat is an exponentially difficult challenge that cannot be solved through reverse engineering or hardware replication. It requires time, investment, and, inevitably, trial and error. The F-35's own history, plagued by cost overruns and delays tied directly to software maturity issues, serves as a vivid analogy for the systemic difficulty of this process, even for the most established aerospace industries. For the J-36, this digital debt translates into a critical operational vulnerability. The pilot may receive data that is fractionally delayed, slightly less precise in location, or ambiguously integrated, potentially slowing the crucial decision cycle in a high-speed, beyond visual range engagement determined by milliseconds and data integrity. The Chengdu J-36 is a platform defined by calculated trade-offs. Its design successfully incorporates key features necessary for a potent fifth-generation fighter. It boasts superior kinetic performance with an estimated maximum speed of Mach 2.0 and genuine supercruise capability. It possesses a massive internal magazine capacity, able to deploy 6 long-range air-to-air missiles while maintaining stealth, and it achieves a respectable, if not class-leading, low radar cross-section signature. However, these strengths are balanced by clear technological liabilities. The choice of twin, high-thrust engines necessary for its speed results in a pronounced thermal signature, making it susceptible to passive infrared search and track detection. More strategically significant is the relative immaturity of its sensor fusion software. Until this digital gap is bridged through years of iterative, combat-validated refinement, the J-36 will operate with a measurable tactical disadvantage in situational awareness compared to the F-35. A final, often underestimated factor in this rivalry is logistical footprint and cost. Western military programs are notorious for high operational and support costs. The F-35A, for instance, incurs an estimated direct cost of $42,000 per flight hour. Such high costs severely constrain training hours and deployment frequency. If the J-36, relying on indigenous systems like the WS-19 engine, can achieve significantly lower operating costs, even a fraction of the F-35's, the People's Liberation Army gains a major strategic advantage. Operating cheaper allows for higher sortie generation, increased training hours, and the ability to field larger numbers of aircraft globally, effectively using volume and persistence to compensate for technical shortcomings in specific metrics like radar cross-section or software maturity. Finally, the ultimate operational effectiveness rests with the human element. The J-36 is being rapidly produced, with serial manufacturing ramping up, allowing China to field dozens of these aircraft quickly. Yet, all the advanced engineering, stealth geometry, and powerful engines are ultimately reliant on the pilot. Analysts consistently note that China faces a profound deficit in high-end training ranges, complex multi-service exercises, and most critically, the real combat experience that has refined Western tactics and systems over decades. A machine may catch up in hardware in a decade, but building a pipeline of highly proficient, combat-ready fifth-generation aviators requires a generational commitment to continuous high-intensity operation that cannot be reverse-engineered. The J-36 represents a phenomenal leap in China's indigenous aerospace industry, successfully tailoring a high-performance stealth fighter for its maritime ambitions. While its hardware capability is clearly closing the gap, the true future margin of air superiority will be determined in the invisible realm of thermal management, data integrity, and the enduring human factors of experience and tactical proficiency.